Hey guys, and welcome to our bubble sort sorting algorithm tutorial series. In this video, we'll take a look at bubble sort and how it actually works. So this is actually part of an entire series where we're going to be discussing almost 10 different sorting algorithms and their inner workings. And bubble sort is the first video in that series. So why did we start off with bubble sort? Well, it's because it's actually pretty simple and easy to learn. All right. It's just about anyone can learn it, and there's no deep logic into it. It's just simple comparing and swapping. That's all there is to it. Of course, this does mean that it's not exactly the fastest, but we'll get more into that later. So this video is basically divided into three parts. The first is a worked demonstration of how bubble sort actually works. We'll actually show you visually how bubble sort sorts in an array or a list of numbers. The second part in this video will be where we actually discuss the code, and in the third we'll generally discuss the bubble sort algorithm and how it actually compares to other sorting algorithms. All right, so let's get started. All right, so this is the list of numbers that we'll be sorting. All right, now before we actually proceed, I want to briefly explain how bubble sort actually works. So it uses two for loops, right? Two nested for loops. So let me start with the second for loop. Now the second for loop is in charge of individually iterating over each one of these elements, all right? So basically it iterates over these 7 elements, all right? The first for loop, on the other hand, is in charge of repeating this process, repeating this iteration process, iterating over each element. I like to call this passes. So it's in charge of making passes over this list of numbers. And the number of passes is always n minus 1, where n minus 1 is the length of, where n is the length of the list of numbers, in this case 7. So why do we make so many passes? Well, that's just how bubble sort works. One pass itself is not enough to sort the array. You actually need to make several passes throughout, and we'll be using I to represent the first for loop, like for I in range n minus 1, and we'll use j to represent the second for loop. All right, you'll see that over here, all right, where we actually begin sorting it out. I've included the indexes over here as well, so you can actually see the indexes change as we sort the values. All right, so what is j plus 1 here, and what is j? Well, j, I told you before, is when we're iterating over the array. So it is actually 0 at the start. It's pointing to the first index, pointing to the first value actually. First index is actually, indexing starts from 0, so the first value is stored at the 0th index, and the second value is stored at the first index. Okay. So what is j plus 1, and why are we doing this? Well, j plus 1 is actually used in comparison. The second for loop, within the body of the second for loop, what we actually do is that we compare j and j plus 1. So what are we doing here? Well, j plus 1 is actually the next value in the array. We can see that over here. 3 is j, and j plus 1 is 8. Okay, so how is this relevant? Well, we want to compare these two and find out if they're sorted or not. And how do we know if they're sorted or not? Well, if the value ahead of j, if j plus 1 is greater than 3, we know that it's sorted. Or if if j is smaller than j plus 1, all right? Both is fine. You can either compare it like if j is less than j plus 1, or if j plus 1 is greater than j. That's up to you. Okay, so over here we can right now clearly see that these two values are in their sorted position because 8 is greater than 3, so we're not going to do anything over here. So what would we do if it was not sorted? Well, we would actually swap the positions of both of them, and we'll actually see that soon. Okay, look, so we're gonna actually proceed further because there was no change, right? So we're just gonna continue on without doing anything. 8 and 1. Now here we can clearly see that it's not sorted. 8 is larger than 1, or if you want to look at it the other way around, 1 is smaller than 8. Okay? So what we do actually is swap the two of them. Okay, so take a look over here, 8 and 1. So we swap them, so now it's 1 and 8. And then we proceeded onwards, all right? So now j is pointing to 8, and j plus 1 is pointing to 3. And 3 is the third index, all right? This is all indexing over here. And the I is equal to 0 here actually represent the number of passes. So we're still on the first pass, all right? Just keep that in mind. So 8 and 9, that's sorted, so we're not going to do anything here. We're going to proceed. Okay, so 4 and 9 was actually not sorted. You can see that over here, 9 and 4, all right? So I just directly swapped the two of them here. Okay. Now let's move on. So we swapped 6 and 9. Okay, you can see that over here, there's 9 and 6. So we swapped that to 6 and 9. I'm actually not including some transition, some in-between slides, all right? Because otherwise we would end up with like, 100 of them, okay? So yeah. And then again, there'll be another swap between 9 and 2. You can see that over here, 9 and 2 have been swapped. Okay, so this marks the end of the first pass of the bubble sort algorithm. So clearly the list doesn't look any more sorted than it was at the start. So let's wait for another pass to occur and see what it looks like, all right? Okay, so this is pass number 2, which is why I is now is equal to 1, all right? And again, we reset j is equal to 1 and j plus 1. You don't need to reset that, obviously. It's all being handled due to the for loop, nested for loops, all right? So 3 and 1. Now 3 and 1 is obviously not sorted, so we'll swap that. And now we have 1, 3. Now, of course, I've actually not included that in-between slide again, so I've directly sorted 4 and 8 over here. Okay, you can see that 8 and 4 was here, and now we've swapped 4 and 8. Okay. And again, I'm updating the values over here so that even if I skip an index or two, you can see things change over here. Okay, so the next comparison will be between 8 and 6. You can see that compared over there. We've swapped the two of them. Okay, and now we can already see that our list of numbers is somewhat sorted, right? It's about almost half sorted by now. So the next comparison is between 8 and 2. We can see that here. We've swapped the two of them. Okay, and the next comparison will be between 8 and 9. Again, nothing to do over there. So let's just skip ahead to the second pass. Sorry, I mean the third pass. Okay, and again, j and j plus 1 have reset. Okay, so now we'll check 1 and 3. There's nothing to be done over there. All right, so let's skip ahead and look over here. 2 and 6. This was the next change. Now I'm skipping the in-between slides again, all right? So don't be confused if we jump between indexes. I'm just skipping those because there's no point in showing them when there's no change. I'll just show you the swapping, the swapping parts now. Now the next swap occurs at pass number 4, okay, between 2 and 4, okay. The next, again, look, there's no swapping gonna occur here. There's no swapping between 4 and 6. There's no swapping between 6 and 8. There's no swapping between 8 and 9. So we'll just skip ahead to the the fifth pass. Again, and we swap 2 and 3, okay? Because you can see here that 3 and 2 weren't sorted, so we swap 2 and 3, okay? And yeah, that's about it actually. This is the last slide. We now have a fully sorted array. Okay, so if there's one or two things you'll have noticed throughout this sorting, was that as the number of passes increased, the value of j never went past a certain point. Take a look. This is roughly the starting. Okay. Now just watch the value of j, the indexes of j. Okay, it goes all the way to the end over here. But now as we progress, okay, it stops going past a certain point. Look, over here, it hit the second last, all right? J plus 1 touched the second last value. But as we proceed, it doesn't even do that, okay? It keeps lowering its search range. Now, how is this relevant? Well, you'll see that as we discuss the code, okay? So let's actually move on to the code now, okay? All right, so as promised, here's the code for the bubble sort algorithm. And as promised, it's pretty simple. So we can see here that the array, we pass it into the bubble sort function, and then we find out the length of the array over here, and then here are the two for loops, and then here's the comparison code, all right, to see if j is actually greater than j plus 1, in which case it means that it's not sorted. Now, of course, I mentioned earlier that you can also reverse this logic and just do this. So if j plus 1 is less than j, which obviously again means that it's not working, and of course it'll sort itself perfectly fine, all right? It doesn't make a difference, okay? And you'll see with this, it also sorts it perfectly fine. So you may be wondering, what is this over here? What is this n minus I minus 1? Well, it's actually nothing complicated. Okay, well, it is a little bit, but what is the minus I here for? So before we get into that, let me just explain what the minus 1 here is for. Well, it's here because we don't want to access the last element in the array with j. Okay, because the reason behind that is because we do j plus 1. So imagine this, if j was able to reach the last index in the array, then our code would try accessing j plus 1 as well. And that doesn't exist, right? Because there's nothing past the last index, which is j. So that's why we do minus 1, because j plus 1 will automatically include that last index in the comparison, all right? So don't worry. So okay, yeah, back to the minus I. Look, I'm not going to spend too much time on this because it's just a performance trick. Look at this, you can see that if I remove it, it'll still work perfectly fine. So what does it really do? Well, it reduces the number of redundant comparisons and swaps that we make, all right? Because you'll notice that, well, if you paid close attention, you'll notice that the swapping, as the number of passes increased, the range in which the swapping was occurring also decreased. This is because as the number of passes occur, as the first pass happens, the second pass happens, the third pass happens, the end of the array, because it's being sorted, it becomes sorted, all right, fully sorted. After the first pass, the last element of the array is sorted. After the second pass, the last two elements are sorted. After the third pass, the last three elements are sorted. So there's no need to actually go back and compare those anymore. So that's why we do minus I, to actually, tell the code that don't bother checking those, all right? So as the number of passes increase, we basically decrease the range of j, all right, to ensure that it doesn't go over there. And let me quickly show you this in the slides over here. Now just pay close attention to the end of the array, all right? Now, this is the end of the first pass, all right? Now we can see 9 over there. 9 is sorted. Now, this is the end of the second pass. We can see that 8 is now in its correct position. This is the end of the third pass. We can see that 6, 8, and 9 are in their correct positions. There's no need to swap anything over there. There's no need to compare anything over there. So yeah, that's why we do minus I, okay? So now what's up over here? Well, this might seem a little strange to some of you, but it's actually the Pythonic way of swapping elements, right, in a list. Now, actually not swapping just elements in a list. You can use it to swap anything, all right? The general format is like this: A, B, all right, and B, A, okay? So basically what happens is that you swap A with B and you swap B with A. Now, the reason why we do this is because if we were to do this in the regular way, which is how we would do it in other languages, is that we would first create a variable called temp, okay? and then we would store one of the values over here, okay? Either j or either j plus 1 or either j, it doesn't make a difference. And then you overwrite the value of that with j, okay? And then you assign to, hold on, okay. Am I doing this right? Yeah, I am. Let's just test this out. Okay, it works. So yeah, this is the other way of doing it, all right? With by creating an intermediate variable that stores the value. We do this, of course, because the value of j plus 1 is overwritten when you assign j to it, okay? And then we basically use this to store the value, all right? But the Python way of doing things, like this, is actually better, right? Because it's just one line. It also looks nice and concise as well, okay? So yeah, there's actually nothing else to explain, all right? The entire array gets sorted and we return it and we print it out, end of story, okay? So let's just actually briefly discuss bubble sort as a sorting algorithm, how it actually compares its faults and when to use it. Okay, so first of all, bubble sort, it's a pretty slow algorithm, all right, for large numbers. I mean, in a list of large numbers, I mean thousands and tens of thousands, all right? If you want to use bubble sort for just a few hundred, that's perfectly fine, all right? Even up to 1,000, you can use bubble sort, all right? The thing is, bubble sort is a n squared algorithm. N squared, now this is actually big O notation. You can actually take a look at this separately. If you're into sorting algorithms, you should really know what big O notation is, okay? So what does n squared here really mean? It means that because of these two for loops, the bubble sort's time complexity will basically grow at a rate of n squared. The problem with sorting algorithms of n squared complexity is that as the number of items in the list increases, they grow tremendously. By grow, I'm referring to the number of iterations of a loop that happen. All right. So imagine squaring 10, then 100, then 1,000, and then 1,000,000. Now, the square of 1,000 is something that the computer can handle easily, all right? And that goes for anything below 1,000 as well. But as you begin squaring things like 10,000, 100,000, 1,000,000, and which results in stuff like a billion operations, a billion loops, that is that's pretty costly, all right? And that is not ideal, which is why we don't use bubble sort in very large applications, all right? Sorting algorithms that are commonly used for their speed and performance are quicksort, merge sort, heap sort, and there's also timsort, and there's radix sort as well, yeah. So we'll be covering all these and more later on in the series. Just one last thing I want to mention about bubble sort is its best case scenario. Now, the worst case scenario for bubble sort is obviously when the list of numbers is completely randomized, when it's completely jumbled up. But bubble sort has an interesting best case scenario where if the array is already sorted or close to sorted, then the number of comparisons required actually decrease. The number of loops actually decrease. The interesting thing here is that if it's completely sorted, bubble sort's best case scenarios, time complexity actually drops to just n, which is like the best you could actually get. All right, you can get better than that. The important point here is that this actually allows bubble sort to beat other sorting algorithms for lists of numbers that are already sorted or almost sorted. For example, quicksort. Quicksort is actually a pretty fast sorting algorithm, but bubble sort actually performs better than it. It beats it in certain scenarios, all right, which is the ones I just mentioned. So yeah, that's actually one more thing that you should keep in mind. It's not necessarily about just learning one sorting algorithm and then being like, okay, I don't need to know anymore. Each sorting algorithm has its own best case scenarios They have their own different way of handling things. Some of them use more memory, some of them use less, some of them are faster, some of them are slower, some of them do in-place sorting, some of them create new arrays. There's a whole, like, they're all different, right? They're all different in their own unique way. So you should actually know several of them, because then you can use the correct one based on the scenario you're facing, all right? Because it's not just about the speed, all right? Sometimes there are other things to keep in mind as well, all right? So yeah, that's the end of this video. I think we've fully covered bubble sort. We've covered how it works. We've covered alternate scenarios. We've covered optimization techniques. We've covered how it compares to other sorting algorithms. I know this was a little long, but I think that it's necessary to mention more than just the main workings of bubble sort, right? Which is what most people do. So yeah, I just want you guys to know everything there is to know about bubble sort. So yeah, then this is it for this video. I guess I'll see you in the next if you're interested in continuing learning about sorting algorithms, alright? So subscribe if you want to stay updated on our new videos, alright? And I'll see you in the next video.